Okay, so let's talk about bases and coordinate systems. So if you want to go ahead and open up Section 2.8 and get MATLAB ready for your practice and for your notes. And so let's jump right in. So the standard basis for R2, I hope this is familiar to you. The two vectors 1, 0 and 0, 1. And the columns of the identity matrix, which we call vector E sub 1 and vector E sub 2, these are the standard basis for R2. And that's also true for R3 and also for R4, right? The standard identity matrix for R4 is a 4 by 4 matrix with all zeros except along the main diagonal where we have ones. And that's the pattern that goes on and on for R sub n. But notice that we're using these vectors for the basis vectors, right? E1, E2, E3. We're using that same notation regardless of whether we're in R3 or R4. Okay, so generally speaking, that should be clear from the context. If it's not, we actually have to specify what we mean by those vectors. So where are we going with this? Well, it turns out that any linearly independent set of vectors that spans a subspace can form a basis for that subspace. So yes, we have the standard basis that I just showed you, but we can create an alternate basis from any linearly independent set of vectors that spans the subspace. Okay, so suppose we have vectors that live in R3, vectors v sub 1, v sub 2, and v sub 3, and they're linearly independent. Okay, well, we know then that they span a three-dimensional subspace. Why? Because it's three vectors that are linearly independent, so they span a three-dimensional subspace. But it turns out the only three-dimensional subspace of R3 is R3, so therefore this is an alternative basis. These three vectors, because there are vectors that live in R3 and they're linearly independent, they do in fact span R3 and form a basis for R3. And what does it mean? So going back to exactly what the definition of span means, right? It means that there's a linear combination of the basis vectors and any vector in the subspace. So any vector in R3 can be written as a linear combination of vector v sub 1, vector v sub 2, and vector v sub 3. Okay? And I made the point down here that R3 is the only 3D subspace of R3. So in fact, we know that this spans a three-dimensional subspace because there are three linearly independent vectors. So therefore, it spans all of R3. Okay, so let's look at an example. Let's get rid of the ink and look at an example. Okay, so if we're given a set of vectors, v sub 1, v sub 2, v sub 3, determine if that set of vectors forms a basis for R3. And find the b coordinates of w. Okay, so we got to find out if these three vectors in fact span R3. And if in fact it does, we should be able to write this vector w as a linear combination, right? That's what the b coordinates for w would be, knowing that linear combination. All right. So we're going to create this matrix B, which just has the vectors v sub 1, v sub 2, and v sub 3 as its columns. So let's get rid of the ink and jump to MATLAB. Okay, so in MATLAB, we have this nice function, I, EYE. So when we're looking, and this is fairly standard notation, I sub 2 means the standard identity matrix for R sub 2, and I sub 7 would be the standard basis matrix, the standard identity matrix for R7. And I get it by just doing I parentheses 2. Okay. And I can actually grab E1 by grabbing the first column of I sub 2. And I can grab the vector E2 by getting the second column of I sub 2. So you see what we're doing here. All right. And I3 and I4 work exactly the same way. Okay, so here's the example. We have the vectors v sub 1, v sub 2, v sub 3, and we need to determine if they form a basis for R3 and find the beta coordinates, the B coordinates for this vector W. Okay, so the first thing we need to do to determine if the vectors are linearly independent, we need the matrix B, which is its columns are V1, V2, and V3. Okay, and then we row reduce it. Why? Well, we row reduce it to find out that there are 3 pivots. Okay, 1, 2, 3. Why? Because we have 3 pivots, we know that all 3 vectors are linearly independent, right? The number of linearly independent vectors we have is equal to the number of pivots we have. Okay, so we have a linearly independent set of vectors. Okay, and we row reduce. Let me get the W in here. Where is it? I'm going to pause the video and get the W vector. Okay, so you see the W vector is up here. So all I did, instead of coding it some way or grabbing it from somewhere, is I just typed it in, right? So if we use semicolons to separate, then we'll have the W vector is -3, 5, and 2. And then we row reduce B. Let me get rid of the ink. Row reduce B. And we have our 3 pivots. And now we're trying to row reduce the augmented matrix of B comma W. Okay, and then this makes sense. Okay, so we still have our 3 pivots, but notice what we have here. Okay, and again, we have the coefficients of the linear combination of vectors v1, v2, and v3 that is equal to the vector W. All right, let's get rid of the ink and scroll up just a little bit. So what we're saying is, right, that our coefficient C1 is right here. And our coefficient for V3 is right here. And I'm worried about those minus signs. I appear to have, let's just double check. Okay. So here we have this matrix B and this matrix W. I'm sorry, maybe I did it down here. Ah, there we go. This makes more sense. So this up here is incorrect. I got the minus signs wrong. If you'll notice, there was an error. I made the 4 a -4, and I made the -1 a +1. So when we scroll down, this is where I did it correctly. Sorry. And because of these coefficients, the correct linear combination that will produce the vector is 4 times the vector v sub 1, and then 0 times the vector v sub 2 minus the vector v sub 3, and that'll be equal to W. Okay, well, let's check it and see that that's true. Sorry. Actually, what do we need to do? We need some vectors. So V1 equals the first column of B, and then V2 equals the second column, right? So I can change that to a 2, that to a 3, change that to a 2, that to a 3. So now I'll have these vectors V that are the columns, and I have the vector W. Okay, so then I can go below this. Let me get the, and switch to this. Why? Well, because I want to do 4 times V1 minus V3. And I want to do equal and see if that's equal to W. And notice that I get all ones. Okay, so that means that yes, it's true. Okay, so let's do this again, but just see. Okay, so if I take 4 times v1 minus v3 and evaluate it, I get -3, 5, and 2. Well, what is the w vector equal to? And I can get back up here, right? The w vector is equal to -3, 5, and 2. Okay, so we do have a linear combination of the v vectors that is in fact equal to the w vector. And you can see here that it evaluates to -3, 5, and 2 like it's supposed to. So remember that when I row reduce all the way to RREF, that I'll have the coefficients that go in the linear combination that results in the vector W, right? So when I row reduce the augmented matrix, right, I row reduce the augmented matrix B augmented with the vector W, the matrix B augmented with the vector W. When I row reduce that, the solution vector over here will in fact be the coefficients of the correct linear combination so that the vector V, the vectors V, the linear combination of the vectors V that do in fact equal W.